A very useful and generally applicable synthesis of alcohols involves reducing a ketone or aldehyde with a metal hydride reagent such as sodium borohydride or lithium aluminium hydride. In this example, a prochiral ketone is used, which is reduced by either reagent to give a racemic mixture of secondary alcohols. The borohydride reagent is not highly basic, so it may be used in polar protic solvents such as water and methanol. The aluminium hydride reagent, however, is highly basic, so it must be used in a polar aprotic solvent. The alkoxide is then protonated by addition of a strong acid in a second step. Due to the electronegativity difference between boron or aluminium and hydrogen, the more electron-rich hydrides act as nucleophiles and attack the electron-deficient carbon of the carbonyl group in a nucleophilic addition process. The Lewis-acidic boron or aluminium atom will complex with the electron-rich oxygen atom to stabilize the alkoxide. Since there are 4 hydrides for each molecule of sodium borohydride or lithium aluminium hydride, 3 other molecules of ketone may be attacked to give the tetravalent complex shown, which is hydrolyzed in the next step. Since hydrogen is slightly more electronegative than boron and much more electronegative than aluminium, the hydride atoms are electron-rich and thus nucleophilic. If either metal hydride reagent is mixed with an aldehyde or a ketone, the hydride will attack at the electrophilic end of the carbonyl group and the pi electrons will move towards the electronegative oxygen. Drawing the alkoxide as shown, without the inclusion of boron or aluminium, is generally acceptable. Since the starting ketone here was prochiral, racemic alkoxide anions are formed. The relatively low basicity of the borohydride reagent means it may be used in protic solvents, such as water or alcohols. However, the high basicity of aluminium hydride means that an aprotic solvent must be used. For borohydride, not only does the polar protic solvent allow for dissolution of the starting materials, it also means that the solvent is able to serve as a source of acid for quenching the alkoxide anion to give the product. For the aluminium hydride, an acid must be added in a second step in order to quench the alkoxide and produce the alcohol. Overall, aldehydes and ketones are reduced by metal hydrides such as sodium borohydride and lithium aluminium hydride through a process of nucleophilic addition. If a polar protic solvent is used with sodium borohydride, it will serve as the source of protons to neutralize the electron-rich alkoxide. The more basic lithium aluminium hydride requires addition of an acid in a second step. Aldehydes produce primary alcohols through this process, while prochiral ketones give racemic mixtures of secondary alcohols.